best guesses. I'm going back through and reassessing my tolerance for all the guesses. Well, yeah.
So everyone hopefully got the notes that the homework is extended for 2 days because there was a slight mistake. Error, yes. I'm human too. Yes, I was off by an order of magnitude on the capital cost for some reason. Okay, so that'll be due on Wednesday. That's not going to delay homework 3, so homework 3 is still going to come out on Wednesday. Other administrative announcement. I somehow missed that it was President's Day next Monday, so we will have no class on Monday again, which means we're like 2 classes short. So I'm gonna have to readjust the syllabus a little bit. So sorry about that. Yes. I'm gonna, yeah, I need to put that on Canvas, but I'll put a thing that you can actually submit, and I'll make an announcement of that just to remind everyone. So that will be due at the end of this week, right? That's what I said. Yeah. Yes.
You want each of the groups to run the idea past you before you submit, right?
Yeah, you can email me, you can come chat with me. Yeah. Okay. So today we're finally going to start putting all the stuff together that we've been talking about in terms of tools and understanding about the technologies underlying these systems. And we're going to start to put this together into sort of energy systems modeling. So today will be our sort of brief overview of different categories of systems models. And then the next couple lectures will actually do a little bit deeper dive into specific models, kind of covering the different types of categories or common categories for people in this world and doing this type of modeling. Okay, so you guys may remember this slide. It's a general architecture of our energy system. This is kind of what we're talking about, right? So after the first I guess module of the class, right, we have a better understanding of the technologies that lay within our energy system, and then we've talked about tools and techniques that will go into how we systematically cover elements of the energy system in terms of a modeling perspective. So thinking about that, so scoping, so what is it that you actually want your model to examine? There are lots of different energy models out there, and they serve slightly different purposes, right? And so you can think about things like system operation, right? So if I'm thinking of something like, has anyone heard of Plexos? No? Okay. Dang, all right, I thought that you would have, but all right, so Plexos is electricity modeling grid, okay? And so essentially it says, oh, here are all your, you put in data about all of your power plants and you put in data about all of your load demands, and then it'll say, okay, this is how you would operate the power plants, right? And then these are the power plants that you might want to install in the future to meet certain types of loads. So that one is concerned specifically with system operation, and then it has elements of like capital investment and infrastructure deployment, right? And so the context of what you're trying to achieve can really help the decision-making process in terms of what type of model that you're actually going to use. Thinking about the elements of scoping as it relates to spatial and temporal. So are you going to do like some local city area? Are you going to do a state? Are you going to look at the whole country? Are you going to look at multiple countries? And then are you going to do just 1 year of analysis, 1 week of analysis, or multiple decades of analysis, right? These elements are all ways in which you inform your model design as well. So there are, for example, types of electricity grid models that focus specifically on operational aspects, where it covers maybe less time period so that you can get a lot more specific into like hour by hour how things change. But those types of models might be less suited to do things like capacity expansion, where you're like building new power plants and you're going out many decades into the future, because it's just like too computationally complex to go from 1 year to like 25 years. So something like the NREL Reeds model, for example, which would be good for doing capacity expansion. It has some elements of how the system operates like on an hourly basis, but nowhere near the type of fidelity that you would have with a more sort of granular model that's looking at finer areas of time. Okay, any questions about this? Pretty straightforward. Hang on a second. My Dropbox did not update because these are not the right slides. All right, hang on. 1 second.
Do you run working today?
Well, I'm on Zoom, so that part of it is working at least. All right, let's try this again. Okay, there we go. I jumped the gun. I opened it before it synced. I was like, I'm pretty sure I put that later. All right. Well, the model scoping part is important for all of this, but maybe before we jump to that, let me first talk about sort of simple decomposition models. So actually, when we think about this systemically, if you care about sort of really high level outputs, you can simplify elements of this first. And so that's what these sort of simple decomposition models are intended to do. So when we think about the like scoping aspect of it, these are kind of like the least granular things that you can do. So there's a model or approach called Kaya, which are drivers for greenhouse gas emissions. This is greenhouse gas emissions, like one of the most common outputs or metrics that folks care about in the energy systems modeling world, right? A lot of this is motivated by climate change. And so as it relates to something like a high level back of the envelope calculation, I think this has been sort of the first step and introduction into that world. So okay, so what are factors that determine greenhouse gas emissions? So in your guys' own lives, what are some like key choices and decisions that influence your energy use and your carbon footprint? Yeah.
What kind of transport to use? So
Okay.
plane, or what we eat.
Transport, diet. Sure. What else? Yeah. Okay. Heating. Yes. Okay. Cost of these.
Which time of day are you using power in your household?
Okay, great. So time of day. Okay. Do you?
Yeah, I was just feel like where you buy like products and the type of clothes you buy.
Yep. Okay. Where you buy stuff. Okay, great. Yeah. So there are all these types of things, and if we kind of group them together, you can come up with these sort of generic categories of stuff. Okay, and most of these that you guys listed, hang on. So these are the components of the Kaya model. And so most of what you guys listed is in the activity/consumption bucket. Okay, and so this includes things like, right, your transportation, your energy consumption, and like everything lumped into like anything lumped into products that require energy to make, that would be put into here. There was so time of use would actually, so you could consume the same amount but use it at different times. So that actually would speak to this one, the energy intensity and carbon intensity, right? So if you shift when you use electricity, it might come from sort of a lower carbon intensity source. So at a really high level, if we think about these components, you can actually use something known as the Kaya identity in order to do this measurement. Okay, and so it's a really simple way of just breaking greenhouse gas emissions into the product of several drivers. So this framework lets us do essentially like this back of the envelope calculation for what greenhouse gas emissions might look like. So if you have your population, your GDP per capita, right, the average energy used by someone per GDP, and then the greenhouse gas emissions per amount of energy being consumed, right? That gives you a systems level view of the total greenhouse gas emissions across like a population. So activity, right, would be represented by economic activity per capita. You wouldn't get the nuance that we're necessarily talking about, all these individual like things that you could do. We're conglomerating that all into single activity. Energy intensity, energy per unit of economic activity, carbon intensity, right, CO2 or greenhouse gas emissions per unit of energy. And so again, super high level, but what we'll do is we'll sort of hone in more and more as we get sort of larger, more complex models to think about ways we can incorporate all of these ideas that you guys were just talking about. And that pertains not only to activity, but to some of these other things as well. The Kaya identity originates actually from this famous IPAT equation, if you guys have heard of this. So this is coming from famous professors from MIT. Impact is equal to population times affluence times technology. It's a similar type of decomposition method that focuses on the contribution of each of these specific elements to pollution. And so Kaya is essentially a transformation of the IPAT equation into one that's looking not at pollution impacts, but at greenhouse gas emission impacts. one of the really interesting things that comes out of this is that when you think about at a high level, like where the problem is and where the potential solutions are, originally when this sort of first came out, technology was viewed sort of as the problem. And so it was thinking about pollution per amount of production as like the lever that we need to reduce pollution. But that has sort of since changed to think about leveraging this not as not only as the thing to fix, but potential areas where you can have solutions for this. So going back to Kaya, population and activity. So these are socioeconomic parameters, right? So GDP per capita, we usually think of this as, so it's an economic activity per person. It can represent sort of well-being, right? Generally, you know, the wealthier that you are, or the wealthier the average person is, you might consider that as like a higher quality or higher standard of life, but not necessarily, right? And so it is possible to still kind of work with this without necessarily detracting from well-being. And then energy intensity and carbon intensity are socio-technological parameters. So energy intensity depends on type of consumption and production and energy technologies. And this is a big area of possible improvement, right? So if you improve like energy efficiency, that can, for example, lower GHGs without affecting activity. And so your GDP per capita is still maintained. And then same with carbon intensity, depending on the type of primary energy resource being used. If you shift that, you can do that almost independent of some of the other ones. So even at a high level, you might think of this as being like, oh, it's super simplistic, right? But you are still able to identify policy levers within these 4 categories, and what it is that you would want to target if you wanted to, for example, lower greenhouse gas emissions. There are a variety of calculators that you can use online, and this is one of the simplest ways to do sort of projections, right? If you have some sense of what your activity, your energy intensity, or carbon intensity looks like, you can like really easily make greenhouse gas emission calculations, right? So as you change specific rates, what might that do for your greenhouse gas emissions? And so you can play around with some of the models that they have online to look at this. The other nice thing is that the Kaya identity allows you to apply this in different times and in different regions. So regional disaggregation is a nice way of viewing discrepancies in trends that happen amongst each of these categories over time and in different places. So you can see what that looks like. Here, someone has done some analysis using this simple approach to look at projections of greenhouse gas emissions through a variety of different conditions. Yeah.
Isn't the case that Kaya identity also goes to a higher resolution approach as well? So when you look at specific sectors, you do the same thing. So you multiply energy intensity of production with carbon intensity of the fuel you're using and total production.
Yeah, I had some slides about that last year. I ended up cutting those, but there are like a variety of Kaya-like identity equations that are applied to specific specific sectors. So like in transportation, there's a version of Kaya that looks at like carbon intensity of fuels. Yeah, that's right. So it's a nice little simple decomposition tool that you can apply to other things as well. And they'll look something like this. And a lot of the sort of high level benefits that we're getting out of something like the Kaya identity can then be applied analogously to those applications too. Okay. So going back to this thing, and we talked about sort of model scoping, we're starting to want to dig a little bit deeper, right, into aspects of the modeling beyond like one specific output. And then now you're starting to break down the coverage of the model in terms of space and time beyond what something like a Kaya identity would necessarily be able to do. So we're going to break this down kind of systematically, top-down versus bottom-up models. So top-down models focus on sort of macro trends or relationships to describe your overall system. Bottom-up models focus on specific elements or constituent parts of that system to build it up. And then that build up essentially allows you to describe the system in aggregate. And what I'll say about these definitions, right? Like these are kind of philosophical approaches to how I would want to model like a large system. However, practically speaking, at the end of the day, many models, I would say most of the like common big energy system models take elements of both. And we'll see what what I mean in a little bit, right? But this is like a more formalized academic thinking of how we do this. Yeah, but most of the good models essentially have both of these. Okay. And so if I were to kind of break these down, we'll talk about the categories within top-down energy models where you have econometric models. So this is going to build off of some of the like econometrics and forecasting discussion that we had earlier and thinking about the application of that into building a system model. We'll talk about input-output models, and then its close relative computable general equilibrium models, which are also known as CGE models, and then give some examples of those, system dynamics models, and then from the other side of things, bottom-up energy models, partial equilibrium models, which are going to be really similar to the CGE. We'll talk about optimization models. It's, to me, this is a lot of times it's formalized in this way, but optimization models, it's kind of weird to be in its own category because like all the models we just talked about on the last page and most of the models here are all types of optimization models. But okay, we'll get into that more. Simulation models, multi-agent models, and these two are somewhat linked. I would say multi-agent models are kind of a subset of simulation models. Okay, and so let's just go ahead and dive right into it. So top-down models, starting with the econometric system models. So most of these are sort of open-ended macroeconomic models, very heavily reliant on data and specifically like macroeconomic data. So thinking about things like GDP and unemployment, those types of things. When we think about the application of these system models to multiple regions, this can often be a barrier. You know, if a country, for example, doesn't collect the type of data that can be applied, like if they don't have measurements of like unemployment or average income or something like that, then you can run into problems. And also, if the way that they measure those data differ between what you're using to, let's say, like calibrate your model, that can also be problematic. So ignores structure of energy demands. And so your model might break down when structure changes. And so what do I mean by that? So let's say you come up with a really nice econometric model where you take some input values and it gives you some outputs of things that you care about. Let's say it's like energy consumption and like greenhouse gas emissions. And those outcomes are based off of trends that you've seen based on economic factors in the past or something. But then let's say if you're doing this for the US, let's say Congress decides to pass a big like energy bill, like IRA or something like that, right? So they're introducing this kind of like systemic change that could affect a lot of both your inputs and your outputs. Because you are now introducing this type of intervention that hasn't been observed in the past that you can't really sort of capture from the data, that sort of structural change will essentially break your model. Like you wouldn't have necessarily a good way of dealing with that. Yeah.
Can you incorporate those sort of policy interventions into the model using maybe a dummy variable? So maybe the years where you have the kind of intervention, you have one value, and where you don't, it's a 0. Does that capture it in any way?
Well, how would you? I mean, what you are referring to is historical data that does allow you to calibrate it. But I'm saying if you don't have that historical data, right? So if you let's say, for example, like a congressional staffer comes to you and it's like, if we implement this policy, like, what do you predict would happen? Well, if you use this type of model, it's probably not a very robust one to do that type of analysis. As opposed to, we'll see later on down the road, there are some types of models that can handle that sort of thing. Typically, no assumptions of equilibrium. Effects are unidirectional, right? So there are in a lot of these econometric models, you don't have these sort of like feedback loops or yeah, like causal feedback things. That usually is that's usually like a endogeneity issue in these types of models, which you essentially don't want. And so being able to do iterative things into like an equilibrium state, that's not necessarily what you can get with these types of models. And so because of that, you know, econometric models, you can think of more driven as like simple unidirectional relationships.
What do you mean by that?
So you might have something like elasticities where when a price changes, like there's a specific type of response that you would see, but then you don't have feedback loops where it's like, okay, something gets cheaper, everyone has like more income, they inject more money back into the economy that like affects all these things, and then you have to like measure this out into equilibrium. These types of models are mainly like you have the elasticities and you see how things change, and then that's it basically. Yeah.
So is there no way these models would work if there's some sort of reverse causality, or is there a way you could account for that or maybe calibrate it to limit the bias that they
So you can get causality into this, but they're usually not into like a networked endogenized system where everything kind of feeds back to itself. So there will be models that we're going to look at that leverage econometric approaches, but then put them into frameworks that let you do that. But these simpler sort of like econometric system models don't do that. So you can have like simple like decomposition type econometric approaches, right? So this is like somewhat like the Kaya approach. Where you use historical data to estimate changes, right? And so you use these things to actually calibrate coefficients that let you observe elasticities between things like income and energy prices on what energy demand looks like, right? And so this could be like a really simple systems level measurement of energy demand. But you can get all the way to the other end of the spectrum, much more complex. So this is one of the few examples of like just a straight up econometric system model. So the E3ME, so this is a model made by Cambridge Cambridge Analytics, and they have this E3ME coupled with a climate system model and an electricity system model, but the econometric part is just this thing down here. And what I was saying when I meant sort of unidirectional, right? You can imagine that a lot of these things should technically be sort of feedback loops. And they have that a little bit in here. But most of these are sort of unidirectional, and all of these things, each of these arrows might describe like one specific like econometric relationship that they've sort of measured out to look at measures of elasticity. So, okay, if you have a CO2 pricing that increases government income, maybe that will directly correlate with a decrease in income tax, increase in real income, increase in consumption, and so on and so forth, right? And so they've mapped this out for different sorts of regulation. But these are usually some kind of pricing related economic activity that they can actually have some kind of measurable intervention in. I guess what I would say, backing out a little bit at a higher level, the drawbacks of these models have typically sort of led to the development of other types of models that try and take some of the strengths of these things, such as understanding of some of these relationships, but then put them into other sorts of systems that let you be a little bit more flexible and avoid some of the drawbacks. Like even in this case, right, like this has been coupled with other systems models that let it do things outside of the capability of what you'd just be able to do out of just econometric relationships. Yeah.
Do you have an example of how it can be
with this type of model? Well, like here, they are looking at, this particular example is saying, if I put in different sorts of government policies in place, like how would that affect climate change? So that is an example. And maybe this is actually contrary a little bit to what I was saying about policy, not being able to measure policy intervention. So this one is actually doing exactly that, but only policy interventions of a specific type, right? Ones that we have a good understanding of already. So it's not sort of like you can get elasticities for like CO2 pricing because there's like precedent for that. Okay, any other questions about this? So the next one that we're going to look at is related to a couple other ones. So we're going to do a sort of practical, or not practical, we're just going to do an example of this. So the next set that we'll look at is input-output models. So I put here an example. And what I would like to do is to sort of walk through or have you guys help me walk through how we might sort of calculate this. Has anyone ever worked with an input-output model before? No? Okay, cool. You like gingerly raise your hand? Okay, all right. If you think so, then we're okay, because maybe you won't remember the exact nature of this. So, all right. So we have a couple different manufacturers. You have a soda producer, and on the left-hand side is your output, and on the right-hand side is the input. So in order to make 10 cans of soda, you need 1 gallon of water. And you also need, for every 1 can of soda, you need 1 empty can. Make sense? If you are a can manufacturer, in order for you to make 32 empty cans, you need both 1 pound of aluminum, but also for every 1,000 empty cans, you need 5 gallons of water. And so on and so forth, right? So 1 pound of aluminum requires 1.58 gallons of water, 2 pounds of aluminum requires 1 empty can. I guess you're recycling. 1,000 gallons of water requires 5 pounds of aluminum, and 10,000 gallons of water requires 5 cans of soda. So how much does each industry produce in order to make 1 million soda cans? So suppose that you are the soda producer and you need to place orders out to everybody. And then if we tally everything up, how much of each of these other things do we actually need? So you would do this forever, right? Because it's like a circular type of thing. So we'll have a little cutoff, and we'll basically say, we stop placing an order if you request less than 1 unit, either cans, pounds, gallons, whatever. Okay, so let's work through this together. Okay, so I'm starting with 1 million sodas. And how much stuff do I need to make 1 million cans of soda? Okay, so it goes soda, 10 to 1 water, 1 to 1 cans. For cans, you need 32 to 1 aluminum and 1,000 to 5 water. For aluminum, you need 1 to 1.58 water and 2 to 1 cans. And then for water, you need 1,000 to 5 aluminum. And then you need 10,000 to 5 soda.
What does it mean that you need soda cans for water? Is that relationship?
I don't know. I made it up. It just means you need soda to make water. It's confusing, but I've consulted with experts. They tell me, it's
So many Diet Cokes takes with the operator of the water plant.
exactly. Yeah.
Oh, okay.
There you go. There you go. All right. So for 1 million sodas, we definitely need 1 million cans. And then I'm going to put this water thing out to the side here. 100,000 water. To make 100,000 cans, I need yeah, so 1 million divided by 32, which is 31 to 50 pounds of aluminum. And I need another 1,000 gallons of water. Okay, to make 31,250 pounds of aluminum, what do I need? I need cans, and I need water. So this needs 15,625 divided by 1.58, right? Or times 1.58. So 49,375 water. And this needs 15,625 cans. And then the cans needs to be divided by, what is this? No, for 1,000 cans, you need 5 parts of water.
It should be 5,000 gallons of water.
Sorry, where?
Second column, second item would be, right, should be 5,000 water.
Ah, yes. Okay, and then this needs to get added up. Sorry, so let me go ahead and do this. So 400. So thankfully, a lot of these go out back into water. So we'll hold off on all of that for just a second. 214 cans. So then this actually I can stop because it's going to ask for less than 1 unit of water. This will go down to 7.63 aluminum. This will go to some amount of water. Then I have 3.8 cans. And then these ones will both stop because they're both less than 1. Okay. So then I can go ahead and add up all my water. I think this should be something approximately 151, 280 something, 83 gallons of water. And then you can continue on here. So this will go to 756 aluminum and 75.6 cans, and so on and so forth, right? I can continue this chain. Is everyone kind of following along with what's going on here, right? And then you can add all of this up and you can figure out the total amount of cans, aluminum, and water that needs to be produced in order to get to 1 million cans of soda. Okay. So it turns out someone clever figured out an easier way of doing this. And so let's go back here and talk about that. So the clever dude was this guy, Vasily Leontief. Leon Teef. And he actually won a Nobel Prize for this back in the 70s. The application was actually for wartime economics to plan production of tanks, but has been since used a lot in understanding environmental impacts of manufacturing. So it quantifies the interrelationships among sectors on the economic system. So thinking back to our example, right, the interrelationships we're talking about is like for every unit of something, you need inputs from other sectors, right? So that is the point of an input-output model. So you have you form an input-output transactions table, which represents the flow of purchases between sectors. And then you combine that in order to form a transaction matrix for the entire economy. So we'll look at that with our example in just a second. So the basic idea of this is, so Aij, use of material for a process. I is the source, J is the process using the material. So X tells you production of process, and Y is the output of that to find your final demand. So if I wanted X of a material, I would need Y of all these other things. So the idea behind this is you have some sort of supply chain. And so in our example, for a given output, you have your transaction table to tell you how much it is to get sort of 1 unit of that output. And so that's like that first step that we did, right? So if I wanted 1 million, if I wanted 1 million cans of soda, if you multiply against your transaction table, it would then tell you, okay, to get 1 million, you need to have 1 million cans, and then what did I say? 100,000 gallons of water. So after your first level, A times Y, it would tell you how much cans you would need and how much water you would need. Then if you did that again, right, that would tell you all the components of that you would need, right? So for 100 million, or sorry, for 1 million cans and 100,000 gallons of water, you would need this amount of each of the other ones. So that would be your second level. And what we want at the end of the day is the total of everything by adding up each of the steps at each level of the transaction. Does everyone follow? So in our diagram, this would be like the first arrow, the second set of arrows, the third set of arrows, and so on and so forth. And so linear simultaneous equations, you end up with essentially this, okay? And in this process, if you want to, so this is that equation at the end that I just showed. And if you want to go from here to determine what your initial inputs would be to get to your Y, your equation would look something like this. Any confusions or questions or anything. Yeah.
Is the direct requirement matrix computed as a percentage of the total output X or the final demand of the sector Y?
Wait, say that again.
So the direct requirement matrix.
Okay.
So what I'm used to is that it's percentage of the proportions of something that is required to make output of that sector. So the recipe essentially.
It's the input over the output.
Yeah. So it's the X. The denominator is the X to calculate the proportion
No.
for it.
No, no,
the
no.
Denominator for.
It'll become most clear when I show it with the example, I think. Okay, so let's just do that because I think that's the easiest way to sort of understand what's going on here. So the idea is your equation I minus A inverse times Y equals X. Okay, so let's look at what each of these things are. So I is just an identity matrix. So if you recall from linear algebra, I would be, in our example, we have 4 things. So it's just 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 1. Okay. Minus, we have our A matrix, which will look something like this. So inputs and outputs. So we have soda, can, aluminum, water, soda, can, aluminum, water. And on the inside, we have input over output. Okay. So how much soda is required to make soda? No, 0. So if you remember, all we're doing is in here, we're just looking at these requirements. So for soda, you need 10 cans of soda for 1 gallon of water. Sorry, 1 gallon of water for 10 cans of soda, 1 empty can for 1 can of soda. So what that means here, so that would just be 1 over 1 here. We don't need aluminum to make soda directly, but we do need water. Okay, so you need 1 thing of water for 10 parts of your can. Okay, or sorry, of the soda. Okay, for the can, no soda is required for the can. You need 0 here. No cans are required for cans. You need 32 parts aluminum for 1 part can. Okay. And then 5 over 1,000, like this. And I can fill in the rest of this. Hang on. Did I make a typo? I did. Okay. Okay, so that's fine. So then what did we say? We need 5 for 10,000. This will be 0, 5 over 1,000, 0. So you would take the inverse of that matrix, and all we would do is we would multiply 10 to the 6th here. And this operation will give us, oops, tanks, yes.
Abrams.
Yeah, so this will tell you, this might not exactly be right. I might have made a typo somewhere, but these numbers should generally match with the numbers that we calculated in that giant flow table, right? So you can see this way is sort of much simpler, especially as you get to sort of more complex. And you imagine if we had 5 things interrelated, or 10 things interrelated, or a couple hundred things interrelated, you do that chain for years. That's why this dude won a Nobel Prize, because he came up with this thing. So yeah, so this input-output method can then be extended to things like, oh yeah.
I'm assuming this doesn't have a stopping bit built in.
Nope, this is like if you did this out to infinity, right? It would be the like asymptote, whatever. Yeah.
The identity matrix that you showed, the one is reflective of the amount of units of that given the TAM that you want for the output, right? Or is that? I have like a loose memory of this. I'm just trying to.
Mathematical construct.
Yeah, it's just like a math thing.
Okay. It's just a math thing. It is no bearing on the amount of units that I wanted, like, produce.
An identity matrix is useful for a number of things. So in this context,
If it's just a math thing and it's something to create, I can just.
The main thing, right, is that a identity matrix times a vector is equal to that same vector.
yes, but then this one's doing a difference. So I'm trying to like think about the physical meaning of that. Yeah, that's right. This is why I don't have a Nobel Prize.
If it's just a math thing and it's just a construct that's used for this, then read it.
Yeah.
Oh, it's like doing a 1 minus.
Yeah, exactly.
Oh, it's just, yeah, okay.
So the like general idea, right, is like the identity matrix times the output that you want gives you the output. And you want all levels of that. So then in this piece of it, it lets you do the accounting of the first, or the, I guess, 0th level, right, of your needs. It lets you maintain that in your like manual supply chain buildup. Yeah. Because otherwise you would be starting with nothing, or like you wouldn't have your the difference is actually yeah, so if you go here, so this will be 10 to the 6th. And if you didn't have the identity matrix, I think this would be 0. I think.
That is 0, isn't it? That's your input requirements.
No, I think the final one will include your output.
So it's steady state rather than starting from no soda.
This is,
They're being fed into each other, right? You need, like,
yeah, well,
you have to assume it's what it
no, it's this is like the final thing of what has been produced, this matrix. Yeah. I will double check this. Because I made a slight mistake over here. So I'll double check it if that's right. But the idea is basically the high level idea is that once you have your requirements matrix, you can generate basically all the needs to do any sort of one particular output. So what that means is that I can extend that to generalized energy systems across sort of many sectors, okay? And so this is a old transaction model from the 1960s. There are sort of more complicated versions of this now. There's one environmental input output model that uses like 491 sectors by 491 sectors. So it's a lot bigger than this. But right, this tells you that in your like chemical sector, you need requirements from coal mining and natural gas and so on and so forth, right? And so if I were to sort of shift one particular input, let's say whether it's like through a policy intervention that you wanted to investigate, or you're like putting in like a new technology that affects the need for an output out of one of these sectors, then you can see what happens to the rest of the economy very easily, right? So this is a sort of useful tool to quickly be able to get at that, yeah.
What do the non-zero diagonals mean? Refined bullet requires refined bullet.
Oh, you mean on the diagonal? Yeah, that's a good question. So
1624.
Oh, that.
yeah, like these cells. What would that mean? Wouldn't that just go to infinity? I am not sure actually, because usually, well, if the requirements matrix had inputs required from the same sector, any change that puts a requirement on that, oh no, then it just increases. Yeah, it's okay to be self-looping, right? Because then you're just increasing the relative requirements every time you step into your own sector. Yeah.
Isn't there a value added table as well somewhere in there where there's a part where apart from the outputs that you've summed up, we're adding some value to each sector is adding some value? Is that not part of this system?
What do you mean by adding value?
So if you've got, for example, the top says inputs and the rows, the columns are inputs and the rows are outputs.
Yeah.
And if each sector is a coal mining, it's providing inputs to all these sectors, but the output itself, the final output, has some value being added by each sector iteratively. Is that not something that's part of the matrix?
If I understand what you're saying, like the input output matrix would just measure requirements of all your other sectors. It's not necessarily about like value or anything like that. Like, I'm not sure exactly what you mean by value.
It's the original, the other measure that I saw had a table below all this for gross value added essentially. So I was confused as to why that part is not here.
Original? What are you referring to? What
So
table?
these from an LCA class reading I had where it had another table for value added. On top of the inputs that a sector took, the output it made had some value added on top of the materials required beyond the recipe itself.
So you might be talking about a CGE model, which is similar to an input output.
That incorporates the value added by each sector as well.
Kind of, but we don't call it value added. You might want to look at, if you can pull it up. And I'm happy to look at that. So okay, let me move on for now. So the sort of next step of input output, we think about these computable general equilibrium models. So these are derived from the input output approach. So we need to have kind of a grasp of what that's getting at first. So the difference is essentially there's like a greater emphasis on prices, and it allows that to then bring in other components of your, let's say, structure of your societal model, right? And so in an input output, you have some fixed labor to produce iron, whereas in a CGE, that might affect like labor demands due to like changes in wage levels. So a CGE model generally creates this social accounting matrix, which includes your requirements matrix from your input output, but then there are a couple other components of that. And what those components are essentially replicating are things like profits and income factors, and that includes not only the flow of things between sectors, right, but also to government and households, right? So you can almost think of this as this piece as your requirements matrix, and how that affects things within the sector, but then it has all these other sort of loops that can go back and affect things within your requirements matrix. So I don't know if this is what you were talking about, but in
So what I see is the difference between the output, the final output X,
yeah,
and the sum of all the required inputs for that sector. So that difference is the value added. That you're maybe producing final output that a sector sort of brings to market is not just the sum of its inputs. It's on top of that is the creation of that output that's called value added.
oh, so they're just multiplying by some factor.
Yeah, in the end, they're adding it. So if you've got, let's say, sector one needs 200 from one sector and 150 from another, and on top of that, the output, final output that's in its accounting is 1,000. So the difference between that, the sum of its own the inputs it took and the product it got to market is the value added.
I see. So it would be the difference between the 1 million sodas and
All
the
its
other
inputs.
products. Okay. I don't know if I would call that value added, but
And in GDP calculations, they call it gross value added or whatever for each sector.
yeah, okay. I guess, yes. In GDP world, I guess you could call it that. I don't think I've seen that before, but that makes sense. It's just like the overall contribution to the economy. Yeah. Okay, so that is a little bit different from this. So this is a social accounting matrix. This is that requirements matrix from before, but now you have these other things here. And so this is the input-output matrix that we were talking about before, but there are other components. So demand from private consumption, and then the other includes investment, government, and net exports. Here we include elements of labor, capital, and primary energy, taxes, and then there's some like accounting that you can do here. These are like emissions, right? If there are emissions factors associated with these things, you could just calculate that out. So the CGE is slightly more complicated because it has these sort of feedback loops going through additional elements of your economy that aren't just the direct input outputs of the sectors. Everything gets interacted with the rest of the economy, with the government and with households. Yeah, and so this structure lets you, let's say, do a slightly more nuanced version of input outputs, where you are now able to look at like equilibrium, states of all of your inputs and outputs as it pertains to effects on demand, and then those elements, labor, capital, and primary energy. So this lets you do things like look at specific types of policy interventions in like a very structurally different way than, for example, what we were looking at with the econometric modeling. So like here, this is an example where the equilibriums, the CGE was looking at using a carbon tax. And so if you implement a carbon tax into the system, it increases prices for specific things. You can change those in the model, and then see how it filters out to the rest of the economy. And then you can look at your outputs to calculate things like what carbon emissions might do as a result of implementing a carbon tax, right, at different levels. And it looks at, you can break down the effect of a carbon tax to specific sectors, right? So this is one of the nice immediate distinctions that we can see between this approach and like the econometric approach, where the econometric thing might give you a specific like total that might look something like this, and it might even do be able to look at one or two specific sectors if you've like included those explicitly in the model. But with the input output or CGE approach, I can literally see how a carbon tax will affect every sector in that economy, right? And again, so the like much more complex ones with like the 500 by 500 sectors, you can get really nuanced details about the effect of like a carbon tax. Yeah.
In the matrix, the previous slide, if you were to put, add a carbon tax in here, would that go in the primary factors? I guess I'm just trying to visually place where this like sits. It's like a single tax that's applied, and is it done? Where would it put in here?
I think you would put it in here.
Put it
in taxes.
Oh, okay.
So then what you would do essentially is you would have to go in, let's say this was agriculture and this was oil and gas and this is like coal. You could go in here and you could figure out the magnitude that you would need to change these values to reflect to reflect the impact of a specific carbon price on that sector. And once you change these prices, then when you do your calculation for your input output, everything gets updated.
Yeah, so you put in your taxes, calculating taxes for whatever the sector is, so your carbon.
Yeah.
$200 a ton or whatever.
Yeah.
Then the units, whatever the units are, it's adjusting each step.
Yeah.
So
And it's actually not too difficult to do something like that. Like you wouldn't have to manually figure out and like go into a lot of detail, because there's probably somewhere you can find a resource where it gives you like the average carbon intensity of each sector, and then you could just multiply that with the carbon tax. Yeah, exactly. Yeah. Yes.
if you go using like the IRA as an example, right?
Yes.
And the tax credits, right?
Yeah.
That is then placed within the taxes section, and is that reflected differently as or is it?
Like it would be negative, are you saying?
negative?
Yeah, yeah,
It's like there's a negative.
yeah. Not a problem to do that. Yes.
Where would one find the data?
Yeah, actually, because these have actually been fairly prevalent since the 1960s, there is tons of resources where people have already compiled the data for these. If you're asking me specifically, like I could definitely point you to some resources where people have prepared these tables already.
So what's the most difficult part of actually using these? If there's data for the latest code,
Mm-hmm.
models already set up, then like what's the difficult part of going from an idea of what you want to investigate to actually getting some code?
Yeah, so okay, so as far as doing like calculations, like the input output is pretty easy. It's not hard to calculate, right? We do that matrix operation. For CGE, it's a little bit more complicated because it actually does these like feedback things to reach an equilibrium state. And so, I mean, I haven't run any CGE myself, so I don't know exactly what that would entail. But I think that's a separate question. There's a separate question there too, which is like from a practical standpoint, how hard is it to run? Which is one thing. It's not that complicated. But then, like, what are the downsides of the model, right? Which I think is partly what you're implying.
Like, for example, on the subsequent slide, you show this result, right?
Yeah.
So, like, for example, what would have been the difficult part about from going from thinking, okay, I want to know what is the effect of the carbon tax, to actually getting these results? Like, it seems like if it was as easy as just changing one number in an already existing like matrix of
Mm-hmm.
numbers that you got from somewhere else, that it's like really easy.
Yeah. Yeah. It's not that hard to actually carry out and implement. Part of the challenge is some of the data collection piece of it. Although, as I was saying, like it's been done for a while, so you know it might be something like you'd need to update it. But okay, but what do you guys think? Like as far as like a modeling approach, what might be some of the downsides of doing something like this? Yes, exactly. So that's the biggest downside, is that this represents a static view of your requirements matrix of like inputs and outputs. So for example, let's say EVs, right, are hot new technology. They require a lot of like lithium mining, lithium resources. And so you look at your requirements table, and currently like the lithium production and manufacturing process has some requirements across all these other sectors, right? Because they're doing it a certain way. But you can imagine that, hey, that process gets improved and innovated a lot in the future, right? Maybe they'll do less imports of lithium, and we'll start doing domestic production out of the Salton Sea, yes. And so that could change your requirements matrix, and it might look really different, right? And so that is one of the big issues with input output is, and actually a lot of the top-down stuff is that you typically are dealing with more static views of these relationships. Yeah.
So like the hard part then is modeling what your input for this would be based on some technology change or improvement, right? So that's more like a,
Yeah.
How do we think about that? Like,
I haven't actually seen, no, okay. No, there are some hybrid models where they try and do that a little bit, where they will actually go in and update your requirements matrix directly.
right, okay.
But that's like really hard, right? Because now you're saying, instead of just like taking values out of some reference book, now I'm gonna like try and figure out how the oil and gas industry is going to respond to a new mining operation type of lithium, right? And how the agricultural sector is going to change as your lithium mining process changes, right? Like,
Yeah.
so that part would be quite complicated.
But you would if you set it up so you're not like, it's a little more, bounded. So you're doing lithium mining. You're like, I'm not going to worry about agriculture. Right? I'm just going to worry about the direct dependencies and like supply chain. Right? Then it might be easier.
No, because well, that's the whole point of the input output is you care about everything, kind of, right? You want to look at the systemic impacts across everything. So it may be that one of these might be zero, like agriculture might not get affected by lithium, so it'd be zero, but then you'd still want that in your requirements matrix because it's like interrelated with other things that you might be changing, right? The whole point is like, so let's say lithium mining doesn't affect agriculture, but affects oil and gas. And then oil and gas might affect agriculture, right? And so if you didn't include that, then that interrelationship, even though it's like one step removed, would not get reflected.
Right.
So you do want to include things even if they aren't directly associated with the like first step process.
Right.
Yeah. Yes.
There are models out there that try to do forecast modeling on individual terms of the metrics like this.
Yes. Some of the hybrid models that I'm talking about, yeah, will combine like CGE and econometrics and some of the optimization stuff. Yeah. So like I was saying, in practice, a lot of these models aren't just like a CGE model. It's like a hybrid system of many kind of things, elements of each of these sort of more like pure way that we're talking about the systems modeling right now. Yeah.
So does a carbon tax alter the direct requirements depending on which sector you're looking at? Is that what it's doing when you model it as a policy dimension? What is actually
No.
changing in this carbon tax?
These things and these things. Your demand and then your labor capital and primary energy elements.
And is the demand determined by those matrices, or is it given outside the model?
No, it'd be your baseline demand would be like an exogenous input.
Exogenous. So
Yeah.
That's what's changing when there's a carbon tax.
Yeah.
And that in turn affects the sectoral decomposition, as you saw in the chart.
The
Next chart, yeah.
this thing.
Yeah.
Yeah.
Okay.
Great. So CG basically taking input output to the next level. All right. System dynamics models. This is like categorically quite different from what we've looked at before. I haven't worked with these much, but kind of interesting. So this looks, to me, this is almost, this can almost be classified also as like a bottom-up approach. Depends on the context of your system dynamics, but looking at interdependencies on dynamic changes over time. And the whole point is that this type of an analysis is the type of thing that builds off of the econometric approaches to look at causal identities through feedback loops. So an example of this. So in our like econometrics approaches, we usually think of like some explanatory variable affecting a response variable, right? So your independent variable, dependent variable. And when you do causal diagrams for common econometric models, they're unidirectional, whereas these ones have all sorts of like interconnected causal relationships that have feedbacks. And so you have to do these like really nonlinear differential equations to like solve these types of things. This is like an example application to new technology adoption. Actually, if you look at this, does this remind anyone of anything? Huh?
The normal distribution, that's the adoption.
Yeah, the diffusion of technology. So specifically with this one, innovators, imitators, this is the Bass diffusion curve type of thing. And so you can see here, like the system dynamics, it like draws from a population of potential adopters, which is one portion of this curve. And that saturates up, right, to everyone. And then that's broken down into, innovators versus imitators. And you can see how that relationship looks in this systems dynamic model. Honestly, I don't really do anything with this stuff. It's a little too complicated for me.
I was gonna ask, like, I don't see, like, if you were to show someone this, I don't know, like, what are they gonna take away? Like, there's no.
Okay, so,
It's like
okay.
it looks like an animation of a model that you could just be like, here's, here's a data table that shows it.
Yeah, so,
TX to
yeah, exactly. No, okay. This is trying to slightly open up the black box a little bit. So what you're actually seeing here would be a description essentially of what the differential equations would be plotting out. As far as like inputs and outputs type of thing, this wouldn't be too different from any other sort of systems model where you could just take the results and describe like, at this time period, we expect this many people to be adopting the technology and so on, right? But yeah, it's a little bit complicated, like how they came up with a particular answer, right? And like people have gone absolutely nuts with this stuff. No. So like this is a very actually, somewhat complex set of differential equations for this set of relationships. So I like can't even imagine what this looks like. Yeah. And so these all have like crazy feedback loops embedded throughout. And so, but you can apply that type of thinking and approach to these system dynamics models. And if anyone's interested, like I don't think they teach anything related to systems dynamics here at Davis, but there is like literature out there. There's some resources. So if folks are interested in this area, I'm happy to provide more resources. Okay, so that is top-down models. And we can talk about bottom-up models. And what I'll say is, for a lot of this stuff, we're gonna look at sort of more practical examples of real models that have been implemented in a little bit more detail. So like today is really meant to be kind of a higher level overview of these different approaches. Partial equilibrium models, very similar to CGE models, but partial equilibrium models assess only a single or subset of sectors. So as you were saying earlier, right, if I just wanted to look at one particular thing, you know, maybe you don't care about like agriculture or something. Whereas I was kind of naysaying that in terms of the CGE, the trade-off, right, in being able to look at holistically the full economy is that here I can like really introduce more nuance for specific like technological detail. And that's a really big benefit in my mind. I think that, so personally speaking, I think partial equilibrium models are like way more useful than CGE models because of this. And there are a couple examples of these models. Yeah.
When you run these, it's like the agriculture example, like you are not including it, but is it like all else equal approach? You're saying like it's gonna be one no matter what. We're saying it's one, and we're just looking at this.
Kind of. You can do it in ways that you're not totally ignoring it, where you just treat other things outside of what you're looking at as like static, and so it may still have some relationship, but it's not a relationship that is like dynamically updating in any way.
Is this also like, I don't know if this is the right way to describe like strong and weak relationships? Can you like tune it such that it's like we still want to see what happens, but we're going to make it a really weak relationship because we're not, obviously something's going to happen. We don't really care how much what happens specifically. That's not the focus, but we're going to make it a weak relationship.
Maybe, I'm not sure. Like, I think if you're including an aspect of it, then it's like in the model.
Right.
Like, I don't know what it means to be like strong or weak necessarily. I think like if you've included the relationship, then you are modeling it to some extent.
Yeah, I guess what I mean when I say strong or weak, perhaps there's a different word to describe it, but saying that like in this scenario of our model, we're assuming that lithium mining is going to like massive ripples in agriculture for some reason, whereas another one's going, yeah, not really. Like it's weak.
You could do that with error bars maybe, or a confidence interval of some sort.
It's like that. I don't know. I don't know what I'm getting at here.
Don't literally don't know.
Yeah.
Carlos always your answer.
Yes, yeah, you can do all of these. You could do Monte Carlo, although, man, if the model itself is complex to run, doing a Monte Carlo analysis you might find to be challenging, just because, you know, same thing, you know, if you want to, like for a Monte Carlo to make a smooth curve, maybe you need to run it 10,000 times, but if a CGE model takes like a day to solve, then you're gonna be there for a lot of.
Circle. Pretty good.
Yeah, but that's easier. Yeah.
Really complex models with all those feedback loops. Every loop has some errors. So are you just compounding errors if you're adding more is it even giving the initial output?
Yeah, garbage in, garbage out. Although I guess it might be slightly different. Something in, garbage out. Yes. So, and this is a complaint that I've had with specific systems models, is that sometimes people put a lot of like precision and detail into model that feed into these systems models where you may have things like compounding uncertainty, right? And I think the big lesson there is that being able to identify that type of characteristic of a model where you might have something like compounding uncertainty should lead you to like better strategize like how to do certain things in your modeling. So for example, like maybe you don't need to spend so much time figuring out the exact right input, because like if you were like plus or minus 50% on that input, like it wouldn't really change the output, if that makes sense. So yeah, you should really think about this type of thing in the systems model, like where it makes the most sense to spend like effort and resources given what you understand about how the model works. Yeah. That's something that I wish I thought about more before I like did some of this stuff. Yeah.
I guess behind these, are they like analytical or are they like numerical? Like that's like kind of solution behind individual.
Okay. Input output is analytical. Almost everything else we've talked about is numeric. Yeah. Yeah. I'm going to come back to the partial equilibrium models in a second. Talk about optimization models. Again, almost everything that we've talked about includes some type of sort of optimization in the system. But when we talk about optimization models, system models holistically, typically what these are referring to are system models that leverage optimization to run the whole thing with a specific approach that they want to get the best set of technology choices, which is typically means you are minimizing costs. A lot of times these things are combined with a lot of the techniques that we see in other models. Has anyone heard of Markal or Times? No? These are both really well-known, widely used energy systems models. In fact, I would go so far as to say, yeah, Markal, Times, and Message, these suite of models are probably combined to be, well, these three models are way more popular than any of the other examples that I've talked about so far, right? So these are actually used by like agencies and academic institutions around the world very widely. Yes.
With optimization analysis technology versus can you apply this to policy as well?
Yep.
Same approach or different?
So actually, let's talk about that. So this is the Times model diagram. And so you have some demand and supply. You can put in things like prices and policies. Same here. So this is an optimization system. So, okay, so quick pop quiz review. Like, what are the elements of an optimization? Everyone? Yes.
Decision variables.
Decision variables. Okay. The what? No, that's the regression. Constraints. Yes. And one more thing. What are you actually trying to do? Do you have a
Function.
what's the function called?
Objective function.
Objective function. Yes. So given what I just said about the Times model, so what generically, what is our objective function?
supply side?
Just like really generically. Cost. Our objective in this model is to minimize cost, okay? So you could write this out mathematically, just minimize cost. And the things that allow us to minimize cost is something like how much of a technology I deploy, and then how much I use it. Okay. So that will tell you, oh, and also like how much of the end use technologies that you're going to deploy, right? So like in a really generic, simple way, I might say, take all the oil generators in the model, the cost of that, plus all your gas, plus all of your coal generation, plus your wind generation, hydro, so on and so forth. And I'm gonna add all the operational costs of all those things. And then I'm gonna add up all the cost of all the cars and trucks and buses and trains and so on. Yeah?
Does the cost function that you're optimizing to put a cost like carbon?
So if you wanted to put a policy to do that, you could add an extra term in your objective function and say, I want to do a carbon tax. And so you just add in a carbon tax and you multiply that against all the carbon that gets emitted here, right?
Yeah, I guess I'm wondering more if sort of generic cost is a function of in this case. I'm just seeing that CO2 emissions are around.
Yeah, yeah.
I'm just wondering if that sort of, I know you don't like co-optimization, right?
Yeah.
Two different things, which might be CO2 emissions and cost. So would it be optimization for something that involves the CO2 emissions for a certain cost?
Yeah. So after you add up the cost of all of these things that I just talked about, you could have plus cost of your CO2 price times the emissions coming from this, plus the emissions from this, plus the emissions from this, and so on and so forth. And then now you would have a unified dollar value for in your objective function that you're trying to minimize, okay?
Do you need a carbon constraint then? Because if you're
So this would be a different thing, right? So what is a carbon constraint? That means you're not allowed to emit more than some amount. So that would be a constraint in your optimization. So you could just say, if I add up all the emissions, that has to be less than or equal to whatever your carbon constraint is.
But if a policy like a carbon price is inherently designed that to cap, let's say, the carbon on some level, then we still need to include that, or
No,
the
it
policy automatically?
depends on what policy that you have in here. It's in this diagram, they have a carbon constraint instead of a price, okay?
The price doesn't actually
Yeah.
carbon. If you, the policy was like,
I mean, intended cap, so let's say a carbon
Well-
pricing mechanism is an intended cap on the emissions.
So then you could, so your model, you could do a comparison between what would happen if I enacted a price and what would happen if I enacted a cap, or you could do both, whatever, right? So hopefully this gets you guys thinking about, again, in the optimization world, the structuring of the optimization, right? What would be considered a constraint? What would be considered like a decision variable, right? To build some amount of these things, to operate some amount of these things. If the cost is the minimizing part of it, then wouldn't I just say I build 0 of all of these? Then I would minimize costs, right? But you probably have a constraint in here that says, oh, you have to satisfy your energy service demands, right? So if I add up, all of these guys, then the operation of these, let's say it's in miles or like ton miles or something, it has to like correspond to some constraint where passengers must get X miles, right? So those are all constraints. Okay, and so hopefully that's clear to you guys in terms of how I can structure this thing in such a way that like that corresponds to how we think about and how we described our optimization systems. And in fact, you can see that here. So some models, some hybrid models will do combinations of these things, right? So we have our social accounting matrix. You can see there's a lot fewer elements here. So this is a partial equilibrium model, right? That includes like the capital, labor, and stuff like that from our CGE, but this is smaller, so we consider this a partial equilibrium model. And it could be iterating with a optimization model here, right, which has all of these elements that I was just talking about. So your objective function, and then all of your constraints, right? So this is a capacity has to be bigger than or less than, or sorry, greater than or equal to all your process activities. So that would be like your demands, right? Capacity upper bounds, market clearing conditions, household consumption. So all of these constraints kind of describe the system or a system similar to what we were just talking about before. Yes.
How do these models account for consumer choice?
Yeah. So actually, that's a good question. In the times model here, the end use technologies are simply at different prices, and then service demands are exogenous. But for example, many years ago, in ITS, for example, instead of doing just straight up prices for these, they actually folded in like discrete choice modeling into here so that it was looking at like prices and elasticities and then how consumers would respond, as opposed to just looking at the costs of these. So again, that was a sort of decision amongst the group of people who were doing times modeling here that they wanted to look more specifically at like transportation elements, but then they wanted to, keep it in the context, the holistic context of what times was able to do. And so you can dive into these models and like fiddle with specific components if that is of interest to you. And that's one of the reasons why I like times model, which is a little bit more flexible, has sort of many variants of it across the world. There's like 50 or so different institutions that use versions of the times model. And then, that encompasses us where we have our own version that's, specifically focused on transportation. Yeah, and so it is, yeah, again, thinking about as you, if you're interested in working with these sort of systems level modeling, and once you get sort of familiar with them, with the inner workings of them, there's almost always sort of opportunity to finagle it in ways that, yeah, produce a thesis. Yeah.
And so, in the form that's shown here,
Yes.
it's more relevant to policies that affect the suppliers rather than the consumers. But you could
I wouldn't care. I wouldn't put it that way. I mean, it is a large model that includes many details on both the demand side and the supply side.
see there's only seems to be some exogenous input on the supply side. No, there's demand side.
Here,
Yeah, but
this is inputs on the demand side. That's inputs on the supply side.
what I mean is that where it says policies on the left side and the right side just seems to be like descriptions of the like population and
Yeah, but I think that's just because that's how I may not have put it this way for a times model. That's just that they decided to write it here. So I would think more about any exogenous inputs here that affect essentially anything in here. can be put in, and same right with here. And I think that this is a decent model diagram in terms of being able to give you a picture of like what elements of supply and demand are included. But I would encourage you guys to think about the structure of this in like an optimization context as well. It's a useful exercise to think about the application of that technique, because that is really what it's doing. And in that case, this wouldn't necessarily be the best sort of representation. I would try and think of it more as like the objective function, decision variables, constraints type of, yeah.
Time for a bit. How do these models build in environmental justice? If any?
Yeah, so then environmental justice, we would think about this in terms of like demographics and really spatial scale. And so the extent to which this goes down to spatial levels of disaggregation that you care about, that's how you can inform like impacts for equity and distributive justice and that sort of thing. But that may require you to like rescope the way they've designed, you know, some version of this model. Some may be better suited to look at those types of things. Yeah. Okay, so we'll end here. I'm a little bit over time, and we'll pick up where we left off on Wednesday.
This does like, if you were to say, I want to toss in like the